weird because it looks like it should be an acid, but it is in fact a gas. Okay, so you just need to know that if you see H2S forming in your reaction, that is a gas, not an acid. So let me give you an example of what that reaction might look like. So let's react sulfuric acid with potassium sulfide. Oh, damn it, potassium sulfide. Okay, so let's put these together. We know sulfuric acid is aqueous, but anything with potassium is aqueous. We're going to mix these and we're going to double displace like we always do. So before we do our double displacement, we'll go through and label all of these. What is the charge on H? I don't remember where we were. So we'll start with Paul. What's the charge on H? Okay, sulfate is? Okay, potassium is? Yeah, very good. And sulfide is? Excellent. So now we're going to double displace. So Young, what's one of our products in this reaction? Excellent. You get it, H2S. And that thing is our gas, right? Where did my purple? Oh, still in my hand. Come on, dummy. So I put a G there. So that's our gas. And the other product is going to be excellent. And what's the state of matter of K2SO4? Yep. You can look at either K or sulfate to know. AQ, very good. Yeah, AQ. Is the equation balanced? Haley. It is, great. And so all I want you to see here is that we have our gas, and so we know that that's our gas evolution reaction. Okay, now let's look at another example where it's not so obvious. If a product of the reaction is H2CO3, what state of matter does H2CO3 have, Chloe? Aqueous. Okay, so at first you're like, okay, it's aqueous. I'm guessing the other thing's aqueous. It might be no reaction. But H2CO3 then breaks down into water, which we know is a liquid, plus what atoms remain? If we take out, very good, CO2. And what do we know about CO2? That's our gas, okay? And so because we make CO2, that is our gas. So let me give you an example of how you might see that. So let's say that we react hydrochloric acid with sodium bicarbonate. Okay, so what do we know about both of these? We know both of these are aqueous. Okay, we're going to double displace. So, Suzanne, can you please go through and tell me the charges of everything here? Okay. Yep, that's right. So let's write the formulas of the products. Michaela, what products are we making?
We're gonna end up with H2CO3.
Right, so HHCO3 is the same as H2CO3. Good, and what's the state of matter there?
Aqueous.
Very good, and what's our other product?
NaCl.
Excellent, and is this balanced?
Yes.
It is, excellent. Okay, so if you see two aqueous things, your first instinct might be to say, oh, no reaction, I'm done. But it's not, because what happens to H2CO3, Eliana?
It separates into water.
That's right. So water plus CO2, which is our gas. Very nice. Okay, now another example. If the product of your reaction is H2SO3, then it breaks down into, Valentina, can you guess what it breaks down into? If it's similar to the previous one. Oops. Not CO2, but water and what's not CO2, but what other element do we have? Very good. Water and SO2. Exactly. Water. So we still do that, but then we have SO2, and that right there is our gas. Excellent. So let me give you an example. Let's say we mix potassium sulfite with hydrochloric acid. Okay, so when we put these together, we do our double displacement. Christine, what are our products? You know what, before we do that, we got to list the charges. So just list me the charges first. K is? Okay, sulfite is? Excellent. H is? Okay, now Paul, I feel like I haven't given you any good jobs yet. So write me the products of this reaction. What are we making? Excellent. KCl. Perfect. Excellent. Now, Paul, how did you know it was H2SO3? Exactly. Perfect. Way to read the problem. Loved it. Okay, both of these are aqueous. Young, is this equation balanced? No. How many H's do we need? 2. And how many K's do we need? Perfect. Okie dokie. So what do we do with our H2SO3? It looks like right now that this is a no reaction, but Haley, we know that H2SO3 actually, excellent, which is our gas. Nailed it. Okay, one more. I think you can guess what the products are going to be once we say it. Okay, if a product of the reaction is NH4OH, then it breaks down. Chloe, what did you think it will break down into? Good. H2O and excellent. Ammonia gas. Nailed it. Perfect. Okay, let's do an example. Let's say that we have, oops, what am I doing? Mind your colors, you clown. NH4Cl, and we know that anything with NH4 is aqueous. So ammonium chloride is going to react with potassium hydroxide. And what do we know is that state of matter? What's our state of matter for potassium hydroxide? Aqueous. Very good. Okay, now we need to double displace. Okay, Suzanne, walk me through all the charges. Ammonium is +1, chloride is, potassium is, hydroxide is, nailed it. Okay, what are my products, Michaela?
KCl.
Okay,
And H4OH.
nailed it. Yeah, it is. It is a mouthful. Yep, ammonium hydroxide. Okay, excellent. Now, Kayla, are we balanced?
Yes.
Yes, we are. Nailed it. Okay. Eliana, everything's aqueous. Is this no reaction?
No, there's one of them's gonna.
Which one? That's right. So we're going to make water and ammonia gas. And you're probably like, everything you said makes sense, but I'm a really good student and I like to practice. Oh, you're so right, students. That's why I made you a practice sheet called Gas Evolution Reaction Practice, and you can find that on page 231 immediately after your acid practice, and you can find the key on Canvas. Nailed it. You are such good students. I know how much you love practicing. It's not bad at all, but it is excellent practice for Wednesday's knowledge celebration, because what am I going to ask you to do? Write and balance a bunch of equations, okay? And it's 12 out of the 50 points, so I really want you to be comfortable with it.
That was a great face.
But we also have spent an ass load of time on it. So let's be real. It's important, right? So we have learned 3 reaction types. Precipitation. What do we have to make in a precipitation reaction? Solid, exactly. We learned acid base. What do we usually make in one of those reactions? Water, very good. And then we also learned gas evolution. What do you have to make in those? Gas, exactly right. So those are the 3 double displacements, and you will see those in lab. And I think it's really nice to see them because most of them either have bubbles or a color change. And so they're really fun. Okay, the 4th type of reaction that we're going to learn is single displacement, also known as redox. And before we jump into redox reactions, we have to understand that something different is going to be happening here. So before, in our double displacement reactions, what were we doing? We were just switching places. But what didn't change for any of the things in our reaction? Huh? I thought someone said something. The charges, exactly. And that's a really important thing, that we wrote the charges beforehand and they were the same charges afterward. Now, redox is very different from that because in a redox reaction, the charges change. And that is really important because it tells you a lot more about what's happening in the reaction. Whew. Gotta hydrate. Okay. So when we're doing redox, the charges change because what's happening in the reaction is a transfer of electrons. Okay. A lot of redox reactions that you've probably seen before involve oxygen. So one that I've talked to you about is combustion. So when you burn propane in oxygen, you make CO2 and H2O. And it makes 3 CO2 and 4 H2O. So this combustion reaction is a good example of a redox reaction. And we'll go through and see how the charges change briefly. Another really common example that you've probably seen before is with rust. So if you have iron that starts as just the solid and it reacts with oxygen gas, I'm gonna erase this little guy here for now. What you make is rust, which has the formula Fe2O3 in the solid state. And so this is rust, and that's an example of a redox reaction, right? So what happens in a redox reaction? The reason why it's called redox is because we have both reduction and oxidation. Oxidation is when you have something that loses electrons, so loss of electrons. So the thing becomes more positive. Sometimes I like to say it also gets less negative because people get really confused by this. So I like to think about it in a practical sense, right? If I lose negativity, I become more positive as a person. Same thing with elements and compounds. They lose electrons, they become more positive. Reduction is where we gain electrons. So the thing becomes more negative, which can also mean less positive, right? It'll have a smaller positive charge. And something that's really important is that every redox reaction must have both reduction and oxidation, because otherwise it's not redox. Somebody has to lose their electrons for another one to gain the electrons. And a good way to remember which is Leo the lion says grr. So if you lose electrons, that's oxidation. Isn't that cute? And if you gain electrons, you have reduction. And you might be like, that's so friggin' stupid. But guess what? You won't forget. And some people also like oil rig. Some people know oil rig. Oxidation is loss, reduction is gain, whichever one makes sense to you. But I like Leo says grr. Your choice, I don't care. But whatever you do, just make sure you remember it. So let's go back to the rust reaction. I'm going to rewrite it again down here. So we have 4 iron plus 3 O2 gets F2Fe2O3. Tell me, what is the charge on oxygen when it's in an ionic thing? -2. So what do we have to have on iron? No, think about the subscripts. Iron has to be 3. Very good. Okay, iron started as 0 because any element that's by itself doesn't have a charge. Same thing with oxygen is 0. So oxygen went from 0 to +3, so it lost electrons. Oxygen gained electrons because it went from 0 to -2. So iron got oxidized and oxygen got reduced. So how do we talk about that? We say that atoms that lose electrons are oxidized, and that's what happened to our iron. But if something is oxidized, we say that it is the reducing agent because it made something else get reduced, right? What does a talent agent do? Does that person have any talent? No, right? They're good at getting talented people where they need to be, right? Or a sports agent, can they do sports? No, but somebody else does, and they get them there. The same thing as a reducing agent helps something else gets reduced by getting oxidized. Okay, so the thing that gains electrons is reduced. So what kind of agent is it? Oxidizing, very good, oxidizing agents. So maybe I'll box these two things because they go together. Box that one, box that one. Okay, so we need a way to be able to keep track of the charges right? The same way we did in the reaction we just looked at. And those are called oxidation numbers or states. So we've always called them charges before. And in fact, we're going to pretty much follow all the same rules, but we're just going to add a couple new ones, and we're going to make sure that we're following them in order. Okay, question?
Yeah, so for the rust example, are you saying then because in the formula
Mm-hmm.
to create the right balance, that's what we need. So throw in there. Okay.
So basically what happened is, and this is a great time to discuss it, right? Iron had to get to the +3 state so it could grab oxygen. How did it do that? Well, it gave up 3 electrons, -3 electrons. Oxygen needed to become negative. So then what happened? It grabbed 2 electrons. And when we were able to balance the equation, we ended up at the end with the same number of electrons, which was 12. So there, we moved around 12 electrons. But basically the iron gave them up, the oxygen took them, and then they were able to, right? Make sense? You with me? Okay. So what I'd like to do is go over our rules for how we assign oxidation numbers in a compound. Now, I'm going to ask you about a bunch of these before I even write them in. So every element in a compound or in a formula can be given an oxidation state, and it helps us understand where the electrons are going. And we use our periodic table to help us with that. Okay, so group 1, look at your periodic table at group 1 and tell me, what is the oxidation state of everything in group 1? What charge does it usually get? Group 1, +1. Okay, nailed it, +1. Okay, what about group 2? +2. Okay. What about fluorine and usually the halogens? -1. Good. What about hydrogen? +1. Okay. What about oxygen? -2. Okay, what have we not covered yet? Elements in their neutral state. If we have an element by itself and it's not an ion, what is its charge? 0. Yep. 0. So anything by itself. So for example, iron as the solid has an oxidation state of 0. Oxygen as the gas has an oxidation state of 0. We're not worried about that. We know, okay? Ions, the ion charge is the same as the oxidation state. So there's nothing you have to do fancy there. It already tells you. So for example, if I have K+ and it's the aqueous ion, what is the oxidation state? +1. It gives itself away to you. There's no new information there, right? And anytime we have an ionic compound of group 1 or group 2, we know those are +1 and +2. So there's nothing fancy that we have to do there. Okay, fluorine. But we should put a note. Other halogens will not always be -1. Oops, that should say not. So they can be, but not always. It depends on what they're paired up with, okay? And hydrogen also should be +1. The only time it won't be is if it's paired with, except if it's paired with a 1A or 2A metal. Let me give you an example. If we have NaH, Na is the one that has to be +1. So in this case, what does H have to be? -1. But in every other scenario, it's going to be +1 like it always is. Okay, the most important thing is to follow the rules in order. So the way you see them on this list. Okay. And then the last thing we're going to talk about is that the oxidation states add up to the overall charge. So let me show you how I like to go through these in kind of in order so that I know what I'm doing. Okay, so here's what we're going to do. We're going to do H, Cl, and O. What is the overall charge of chloric acid? 0. It has to add up to 0. So for each of these, what I'm going to do is write down how many of each one I have. And in the box, I'm going to write the charge. So parentheses equals how many of them I have. And the box is the oxidation state. Okay? Then I'm going to use these little sums on the side to make sure that I equal 0. Okay, how many H's do I have? How many H atoms? 1. Okay, let's go in order again. It's more organized. Paul, how many chlorines do I have? Young, how many oxygens do I have? Okay, excellent. Which one of these has its rules show up first in the order? Hydrogen. Thanks, Haley. Hydrogen. So what am I going to put as my charge for hydrogen? +1. Excellent. Okay, so that gives me a 1 total from each. Okay, Chloe, does oxygen have a rule or does chlorine have a rule? Oxygen has a rule, and what is that rule? -2. What is 3 times -2? Perfect. Okay, now the only mystery is chlorine. What are we going to do with chlorine? Well, we've got 1 from H, we've got -6 from O, and what do we have from Cl in order to make it 0 overall, Suzanne? What does this have to be to make this add up to 0? 5. Okay, so that means the oxidation state of Cl is 5. And so here's how you would see it on your knowledge celebration. I would write H, Cl, O, and I want you to put the number in the box into the blank. Does that make sense? So I would just write +1, +5, -2. Okay? So I can highlight this if it's helpful. Any number that's in the box comes down here. Okay, let's do Cr2O7. So Cr and O. What does this have to add up to overall, Michaela? Look at the -2. Okay, so it has to add up to -2. Now, we're going to write down our parentheses and our boxes. So Eliana, how many chromium atoms do I have? 2. How many oxygen atoms do I have?
7.
Okay. Valentina, does chromium have a rule on our list? What's the rule for chromium?
The second one.
Nope, because it's not the rule for, so it's not chromium by itself.
Oh,
So that's a really good point. So the second rule is when you have one element by itself, that tells you its charge. Okay, so we don't have a rule. Do we have a rule for oxygen? What is it? -2. So if we take -2 times 7, we get -14. Okay, so Christine, what do we have to add to -14 to end up with -2? 12. Okay, so if there are 2 chromiums, each one has to be 6. Very good. So if we were answering it like on our knowledge celebration, for CR, we're going to write +6. For O, we're going to write -2 because we take the number in the box and put it down here. Okay, now you do it on the next page. Okay, so identify every element in here. You don't have to use the parentheses and box way. I like it because I think it's helpful for organizing. But again, do your thing. And we're going to look at it in, I don't know, 3-4 minutes. And 0 is a fully acceptable answer. So don't be shy about getting 0. I don't think I gave you a blank one. Sorry.
No, it's okay.
Oh, you know what I could have you do is, I mean, it's kind of cheaty. You can kind of see through it, but you can kind of do it that way, just so you at least have the list over there. Great job. Looks good. Mhm. Yeah. Yeah,
Okay.
that's exactly right. So what we put in the blinks was what was in the box. Yep. Oxidation state, exactly. So what I'm going to point out to you is that Na has its rule before O. So we got to follow this one first.
Okay.
That's a tricky one. Trick. Good. Following the rules in order, team. You're doing a wonderful job. Let's take one more minute to wrap them up. Okay, team, let's look at it together. So, Paul, start us off with bromine. The charges add up to 0, so each bromine has a state of? It should be 0, exactly right. It has to be 0. It is neutral because it's in its natural state. Basically, it's alone. It doesn't have any buddies. It's in its natural state. It's going to be 0. Okay, Young, between carbon and oxygen, which one has a rule that we follow? Okay, and what's that rule? -2. So what does that mean we have to have from carbon? +4, excellent. So that makes our compound neutral overall. Excellent. Okay, Haley, lithium fluoride, which one has a rule first? Excellent. And what is that rule? Excellent. And what's the rule for fluorine? -1. Excellent. And those both work out to give us 0. Okay, potassium ion, Chloe. That's right, because it's +1 overall. Excellent. Question, Christine? Okay. Sulfate, Suzanne, which one has a rule, S or O? O. Okay, so what do we write? -2, so that gives us -8. So what do we have to have for sulfur? +6, excellent, because that gives us -2 overall. Nailed it. Okay, sodium oxide, which one has a rule first, Michaela? Na, and what is that rule? +1. And what does oxygen have to be to give us a neutral compound? -1. So even though oxygen has its rule, which is -2, because the rule for sodium was first, we followed it first. Nailed it. Nicely done. Really excellent work. Okay, I think we need to take 5 minutes to celebrate our excellence. And then I'm going to show you how to write and predict the different types of redox reactions. And then we'll do a boatload of examples together. Oh, that's very smart. No, that's excellent. Yeah, that's also very brilliant. Yeah, those are really nice. I really like those. Just go shopping for school supplies. I don't know. That's always one of my favorite things to do. It's like school supplies, especially when they're fresh. Yeah. I love all the college dorm room stuff they have at like Target and Walmart during back to school. Oh man, I love IKEA also. IKEA is amazing. Nicole Ross? Mm-mm. Mm-mm. What department is she in? Oh. No, I don't. Those guys are kind of a clique. So they're technically under the College of Science and Health. And I was like a fellow for the College of Science and Health to help people with professional development. And those guys ignored me to the max. They came to no events. They didn't talk to me. They were like, we have it. We don't need your help. Thanks, bye. The business schools like that too.
I feel like everyone. We're in high school again. Why? Professor, why?
I don't know. I mean,
They stick within their departments. And
yeah, kind of. A lot of people venture out if they're like, depending on their interests. So like the neuroscience people is a good mix of everybody. I meet a lot of people because I like learning about teaching strategies. So that's a good group from all over campus. But yeah, you're absolutely right. Every department's a clique. But I don't really like my colleagues that much. So I like to meet people from other departments. Because there are a lot of really talented people on this campus in other departments. So. Is it cliquey at Milwaukee too? Probably. I bet the engineering department is super cliquey.
Well, starting out, it's just sort of, you have to sort of.
Yeah.
You have to show that you
Yeah.
can do engineering.
Yeah, that makes sense. You're talking about the game?
Yeah.
Yeah. Okay, so now that we've seen those reactions, let's be able to identify redox reactions. So what you just saw was precipitation. Now we're going to talk about redox, and actually I'll show you a video because those can look really, really neat also. So when we're looking at redox reactions, there are some that are just, you know, where we're changing the oxidation state. So here's a kind of a good example where we're going to react carbon with sulfur. And so just to remind you, when we look at redox, our charges are going to change. So before we identify anything, right, let's look at carbon and sulfur making carbon disulfide. What is the oxidation state of carbon by itself? I don't remember who we were on. How about you, Eliana? What's the oxidation state of carbon? Just by itself, element with nothing, 0, perfect. What about sulfur, Valentina? Element by itself, doing nothing. Perfect. Okay, now we're going to put them together. We don't actually have rules for either of these, but sulfur is in the same column as oxygen. So Christine, what would we think sulfur is going to do? -2, excellent. Okay, so what is carbon then going to have, Paul? Excellent, +4. So let's talk about what happened in this compound. So carbon went from 0 to +4, and sulfur went from 0 to -2. So Young, did carbon gain or lose electrons to become more positive? Yes, very good. So it lost electrons. If it lost electrons, Haley, did it get oxidized or reduced? Leo says grr. Yes, very good. So the carbon underwent oxidation. Okay, so what happened to sulfur then, Chloe? That's okay. Yes, so it had to gain electrons because oxygen or carbon loss, so it underwent reduction. Okay, so the reducing agent is the thing getting oxidized. Which thing is getting oxidized and is therefore the reducing agent in this case, Suzanne? So what's happening to the sulfur? It's getting reduced. The carbon, yeah. It's okay. It's okay, carbon. Okay, so the oxidizing agent is the thing that is getting reduced because it's allowing the other one to get oxidized. So which one is that, Suzanne? Sulfur, very good. So what I want to emphasize is when I identify these agents, it has to be a reactant, must be a reactant. And we'll come back and practice that at another time. Okay, so that's just kind of a generic type of redox reaction.